Welcome. Today we are diving into the fascinating world of eigenvalue decomposition. Whether you are a math enthusiast or just curious about how complex systems work, this video is for you. Eigenvalue decomposition, also known as eigendecomposition, is a fundamental concept in linear algebra. It breaks down matrices into their eigenvalues and eigenvectors. Before we get into the details, let's see some real-world applications of eigenvalue decomposition. The first one being image and data compression. Ever wondered how images are compressed without losing quality? Eigenvalue decomposition helps reduce the amount of data needed to represent an image, making storage and transmission more efficient. The next application is face recognition. Yes, your phone's face recognition technology. That's eigenvalue decomposition at work, analyzing and recognizing patterns in your facial features. Third is the PageRank algorithm. Google's PageRank algorithm uses it to rank web pages. Eigenvectors help determine the importance of each page. Fourth is the recommender systems. Netflix and Spotify use it to suggest movies and music you might like by finding patterns in your preferences. Portfolio and risk management. In finance, it helps manage portfolio risk by analyzing the variance and covariance of asset returns. Control systems. Engineers use it in control systems to design stable and efficient systems from airplanes to robotics. In principal component analysis, it is a technique used to reduce the dimensionality of data. This heavily relies on eigenvalue decomposition. And lastly, quantum mechanics. In quantum mechanics, it is used to solve the Schrödinger equation, helping us understand the behavior of particles at a quantum level. Now let's introduce the concept of eigenvalue decomposition. Imagine you have a matrix, which is just a grid of numbers. This matrix can stretch, shrink, and rotate vectors. However, some special vectors called eigenvectors only get stretched or shrunk, but not rotated. The amount by which they are stretched or shrunk is called the eigenvalue. Let's consider this linear system of equations. These three equations have variable x, y, and z, and they have coefficients from a to I. m1, m2, and m3 are constants. So this system of linear equations can be rewritten in matrix form as shown on the slide. All the coefficients can be clubbed together in form of a matrix as shown, and all the variables, that is x, y, and z, can be clubbed in form of a vector as shown on the slide, and m1, m2, m3, which are constants, are also clubbed together as vectors. So this is a very convenient form of representing a system of linear equations. And as these number of equations, they increase. And why should they be increasing? Basically, each equation is nothing but a data point. A new sample becomes available in the data set, and as a result, a new equation comes into picture. X, y, and z are nothing, but they are the features. They are the predictors which are trying to predict something. And m1, m2, m3 is the dependent variable which these features are trying to predict. That's the data science or artificial intelligence interpretation of these system of linear equations. Moving forward, something really special happens when this matrix A gets diagonalized. And by what I mean by diagonalization is that all the off-diagonal elements are 0 and only the on-diagonal elements are non-zero. When this happens, the three equations that we saw earlier, they get decoupled, in the sense that the first equation is only dependent on x, the second equation is only dependent on y, and the third equation is only dependent on z. So diagonal matrices are a very special kind of matrices, and throughout linear algebra, we are doing one or the other decomposition to arrive at a diagonalized matrix. And we'll revisit this concept when we discuss the eigenvalue decomposition. So just remember, diagonalization is a very, very important feature. Now let's dive into the eigenvalue decomposition. Frankly speaking, it's a very simple concept. Here we have a 2 by 2 matrix represented by 0, 1, minus 2, and minus 3. What eigenvalue decomposition does is that it splits this matrix into three parts, as shown in the figure, by green, blue, and yellow color. And you would notice something very strange happening here. The middle matrix, this eigenvalue matrix, is a diagonal matrix. And that's the reason I discussed the diagonalization concept earlier. This helps in resolving this matrix into independent components. So there are two terminologies in eigenvalue decomposition. One is called the eigenvector. So this green matrix is nothing but the eigenvector. Now this decides the direction of the vectors, and I'll come back to this concept. And these vectors, they do not rotate when this matrix is multiplied by them. And they can only shrink or increase in size, and how much they increase or shrink in size is decided by eigenvalues. So there are two concepts, eigenvectors and eigenvalues. These values which are on the diagonal, they decide how long or how short these vectors they become upon multiplication. And this last matrix is nothing, it is just the inverse of the first matrix. So there are three components, and the idea behind decomposing a matrix into three will become clear in the subsequent slides. So let's go back to our original concept of a vector getting multiplied by a matrix. When we do this, it results in another vector. So in this diagram, the V1 vector, that is 1 and 5, is shown by red color. So we have 5 here and we have 1 here. And this vector is multiplied by this matrix, 4, 1, 2, 3, 2 by 2 matrix. And post multiplication, a result comes out, which is another column vector, which is 9 and 17. And when we plot this 9 and 17, as you can see, this is 9 and this is 17 here. When we plot this vector, you see that it has rotated. The red vector has rotated by some degree, and it has also increased in size. Now this typically is what happens when you multiply a vector like 1 and 5 with any matrix. It leads to rotation, and it leads to increase or decrease in the size of the resultant vector. But there are some special kind of vectors. Now remember, we are still talking about the same matrix, and we are again using the same matrix, but this time we are using another column vector, which is represented by 3 and 3. When we plot this 3 and 3 in green color, here it is. So it is 3 here and it is 3. And when we multiply this 3 column vector, what we get is 15 here, 15 and 15. And when we plot this 15 and 15, you can see that this green vector has only got stretched. It has not got rotated. So this is very, very peculiar. Here, when we are using the same matrix but a different vector, and when we are multiplying them together, the original vector gets rotated. But in this case, we use the same matrix, but we use a different vector, a secret vector or a hidden vector. This is what exactly is called as the eigenvector. In spite of getting multiplied by this matrix, it doesn't rotate. It only stretches in size. It can also get compressed, or it can change direction in the other side. That is, it can go in the other side by 180 degree. But it otherwise does not acquire any other angle. And since it's a 2 by 2 matrix, there are two vectors like this. So the next vector, remember, we are still talking about the same matrix. And here we have another vector represented by this column vector. And when we multiply both these together, we get this column vector. And here again, once you plot these vectors, that is original vector and the final vector, we see that no rotation happens. The green vector is the original vector, and the bluish vector is the rotated vector, which is this one. And the green vector gets stretched out, but it doesn't rotate. Now this is very, very interesting. Let's just recap what is happening here. Firstly, look at the form of this equation. This form of equation has come from the linear system of equations, where this is the matrix and this is the column vector. Just have a look here. Exactly what we're talking about. So all these coefficients are clubbed together in this matrix. And when this matrix is getting multiplied by this column vector, it is trying to rotate this vector. Now, under special circumstances, in spite of this matrix having the rotation effect, there are, in a 3 cross 3 matrix, there are at least 3 eigenvectors which do not rotate when you multiply them with this matrix. And this is this is exactly what is the concept of eigenvalue decomposition. And let's proceed further. So in this slide, what I'm trying to show here is that not only the vectors have not got rotated, so red vector is the original one, and the blue one is the rotated one after the matrix multiplication. This is the first eigenvector here, and this is the second eigenvector. Now just if I plot these two eigenvectors on a single slide, on a single plot, which is here, so just see the direction and magnitude of this red vector, which is exactly the same here in the green vector, and just see the direction and magnitude of this eigenvector, which is here. And when we plot them together, both of them are perpendicular to each other. So what essentially is happening here is that once we resolve a matrix into its components, two things are happening. And this is true for a symmetric matrix. And also, eigenvalue decomposition is valid only for square matrix, which means the rows and number of columns are just the same. So what has happened here is that if I see this matrix has been resolved into 3 components. So these are the 2 vectors which are perpendicular to each other. And this eigenvalue matrix is a diagonal matrix which is stretching or scaling these 2 vectors. This is exactly what is happening. So we have redefined this matrix in this form. And there's a reason, as I told you, when we have a diagonal matrix involved and when we have orthogonality involved in a matrix, then we can decouple the linear system of equations. Let's take an example. So I have a matrix M shown here. This matrix, if it is multiplied by a vector, it should rotate it. So I take this matrix and I decompose it into eigenvectors and eigenvalues. So what you see here are the 3 matrices, 1, 2, and 3. And if you notice, this is a diagonal matrix. And this is what is eigenvalue of this particular matrix. And once we multiply this with this, and then this with this, we come back to the original matrix. Hence proving that this actually is the eigenvalue decomposition. So for the ease, what I've done is that I have simplified these equations here. So this particular is a multiplication between V and L. So this is the V matrix and this is the L matrix. And the intermediate result is this. And then I take this, which is here, and multiply it by V inverse, which is here. And then prove it to you that we started off from this matrix, which is 9 minus 6 minus 6, 8. And we ended up again back to 9 minus 6 minus 6, 8. You can do this calculation by hand. You can pause and take note of the screen. Effectively, what I'm trying to prove to you is that this matrix can be decomposed into three parts. The first part is the eigenvector. There are two of them because it's a 2 cross 2 matrix. And the second part is the eigenvalues, which is a diagonal matrix, which are nothing but the scaling factors for these two vectors. And the last matrix is the inverse of this matrix. Since this itself is orthogonal, inverse is also going to be an orthogonal matrix. And here is the depiction in heat map. So this is the original matrix, and as you can see that different colors are representing different matrices, that is V, L, and V inverse. And look at the color pattern here. We started from yellow, green, and blue here, and we come back to the same matrix here. So this is the visual representation of what's going on top here. And these are the intermediate equations for readability. Now we can do the same thing. Now just pay attention to this. We will plot these two vectors, and I said that these two vectors, once they are plotted, they themselves will be orthogonal to each other. They'll be at 90 degrees. And it's a very important concept. Let's take a 3 by 3 case. Here we have a 3 by 3 matrix M, which is represented by this plot. And I decompose it into three parts, V, L, and L has to be a diagonal, and V inverse. And again, for the clarity's sake, I have multiplied this with this, and the intermediate result is here. So this matrix is here, and this matrix is here. I multiply them together, and I get this intermediate result. And then I take this matrix here, and multiply by the last matrix, which is V inverse. So this into this, and I come back to my original matrix. I started from 17, 8, minus 6, and this matrix M. I come back to exactly the same matrix. So I have been successfully able to resolve this matrix into three parts: eigenvectors, eigenvalues, and the inverse of eigenvectors. And you can very clearly see from the color pattern that the first and the last plot are just the same. And here once again, I plot these eigenvectors together on a plot, and you can see it here. So this is my coordinate system. The dashed line is my coordinate system, and when I plot these three vectors, they turn out to be perpendicular to each other. Now, how do we go about interpreting this? So there are two interpretations. One is the geometric interpretation, which talks about non-rotation of eigenvectors because of multiplication by a matrix. And it says that if you have a 2 by 2 matrix, there'll be two eigenvectors. If you have a 3 by 3 matrix, you'll have three eigenvectors, and so on and so forth. So that's the geometric interpretation, which is mainly concerned with non-rotation of vector because of multiplication. Essentially, within a matrix, there are some hidden vectors which, in spite of multiplication, they don't rotate. They can only get scale up or scale down. Now here is a statistical interpretation of the same thing. What I'm showing here is that there are two random variables, d1 and d2, and I do a scatter plot. And just by looking at scatter plot, I see that there is a correlation between these two variables. So when d1 increases, d2 also increases. And the same relationship is captured by this covariance matrix, where diagonal elements are variances, which is the measure of how spread out the data is in this direction and this direction. And then off-diagonal elements are covariances. And it's a very big number, which clearly shows that there is a correlation between both the variables. And we can actually see from the visuals that when vector d1 is increasing, vector d2 is also, random variable d2 is also increasing, indicating that both of them are strongly positively correlated. But if we can do something, if we can find hidden excesses inside this data, excesses which do not rotate when multiplied by matrices, then we have found the hidden excesses, which are also called as principal components. So we have one principal component which is going in this direction, and one principal component which is going in the other direction. Essentially speaking, instead of looking at the data from this angle, from this coordinate system, I find the principal components or the hidden excesses inside the data, which are principal components. And once I have found those excesses, I rotate them. For example, I rotate this whole thing vector and make it vertical. And because of that rotation, this vector will become the horizontal vector. And you see that this entire data set will rotate. Once the data set rotates, as you can see that there are some points here, and the same points now appear here. And there was a point here, the same point has appeared here. So what has happened here? What I have done here is that instead of making a scatter plot between d1 and d2, I have made the plot between the principal component 1, that is this, and principal component 2. And this has led to the rotation of the entire data set. But why would I like to do that? Once I do that, something very interesting happens. Even when I'm going in this direction, my data spread or my data correlation is 0. going in this direction does not impact my data. Similarly, when I move in this direction, it has no bearing on the other axis. Essentially speaking, this rotation has decorrelated the entire data set. So it's another way at looking at data. And now when I do the covariance matrix calculation, you will very clearly see that the off-diagonal elements have become 0. That means the correlation between them have disappeared, and the on-diagonal elements are nothing but the individual variances. So as you can see, variance in this direction, that is spread in this direction, is very high, which is represented by this number 25, which is the variance in this direction. And spread in this direction is not that much, which is the variance in this direction, and that is represented by this small number 2.5. And hence I've been able to decouple my system. The interdependency between these 2 points have disappeared because I've been able to find hidden excesses inside this data, and using those excesses I've rotated this data. Essentially speaking, I'm looking at this data from a different angle, and when I look from that different angle, the interdependencies or interrelationship between these 2 variables, they disappear, and now I'm able to slice and dice this data in a much better form to get better insights. So I'll give you a rough analogy. It is Rubik's Cube. So if I look at this Rubik's Cube from say this coordinate system's perspective, this axis, and this axis, it looks pretty jumbled up. And just compare this with the original matrix M, which is represented by this cube. However, there are hidden excesses inside this cube, which are these rotation excesses. And these rotation excesses, once I have found these rotation excesses, I can move these surfaces independently, and these excesses will not rotate. And hence, I'll be able to achieve all the colors on one side because I have found the hidden excesses inside this Rubik's Cube. And these hidden excesses or the rotation excesses are nothing but the principal components of this data set. And decoupling means that I can move one surface independent of the other surface. So I can move this up surface independently, and then I can move the other surface also independently. That's exactly what happens, and this is exactly what eigenvalue decomposition is achieving this. If you remember, we talked about decoupling of equations because of diagonalization, and now all 3 equations have become independent of each other. And now I can do some changes in one coordinate system or on one axis or in one equation, and it won't impact the other part of the data set. And hence I have found the hidden modes inside the system. We will explore these concepts in more details, and we will talk about some certain applications where this is used. That will be the next tutorial, and I'll be using Python to demonstrate application related to stock investment and portfolio management. I'll see you in the next section. Thank you so much.